Hey everyone, welcome to this explainer. Think of me as your ultimate digital tutor for CS604. We're gearing up for the virtual university exams, and honestly, we're cutting out all the fluff today. We are going to strictly focus on the exam point of view and hone in on exactly what you need to know to pass.
Let's just set the record straight right off the bat. Literally 90% of your conceptual and practical paper, it comes directly from these exact core algorithms and commands. No joke. So if you really want to crush the final, you're going to want to lock these down. Listen closely, because mastering these is basically your secret weapon.
All right, here's our high-yield blueprint for today. We'll run through the critical section problem, semaphores and deadlocks, memory management, disk scheduling, and we'll wrap up with the exact high-yield exam numericals you're going to face. Let's get into it.
Section 1. We are diving straight into the critical section problem.
You are definitely going to see this on the test. Think of a critical section kind of like a single fitting room in a clothing store, right? Only one person can be inside at a time. In your code, it's that specific part where shared resources or shared data are accessed. The absolute golden rule here? Only one process gets to execute in there at any given moment. This is the entire foundation for avoiding data inconsistency or, those nasty race conditions when multiple processes try to grab the same resources simultaneously.
So to actually solve this problem, we have 3 incredibly strict requirements. And seriously, commit these to memory because they pop up constantly in the short questions. First up, mutual exclusion. Basically, if one process is in its critical section, no others are allowed in, period. Second is progress. If the critical section is empty, we shouldn't unnecessarily delay picking the next process to go in. And third, bounded waiting. There's got to be a hard limit on how many times other processes can just cut in line before a waiting process finally gets its turn.
Moving on to Section 2, Semaphores and Deadlocks.
Now, semaphores are essentially your synchronization tools. They're just integer variables that control access to shared resources using wait and signal operations. For your MCQs, you absolutely need to know the difference between the two types. A binary semaphore is locked into just 2 values, 0 and 1. Which makes it perfect for strict mutual exclusion. A counting semaphore, on the other hand, operates over an unrestricted domain, so it's used when you're dealing with a pool of multiple identical resources.
But what happens if that synchronization completely fails? Well, we hit a deadlock. It's the dreaded system freeze, where processes just end up waiting forever for resources that the others are holding. Now, for a deadlock to actually occur, 4 specific conditions have to happen at the exact same time. We're talking mutual exclusion, hold and wait, no preemption, and circular wait. The trick here? If you break even just one of these conditions, boom, you prevent the deadlock entirely.
Please, whatever you do, do not confuse deadlock with starvation on the final. Deadlock is when processes are waiting forever for each other in this endless closed loop. Starvation is a bit different. It means a specific process is waiting indefinitely simply because the resources it needs keep getting handed out to other processes. So it's not a loop, it's just really bad luck for that particular process. All right, Section 3. Let's pivot to memory management and how the operating system actually allocates your RAM. When you get to those detailed, long questions, you have to be able to contrast paging and segmentation perfectly. Think of paging as highly mechanical. It divides physical memory into fixed-size blocks called frames and logical memory into pages of the exact same size. This completely gets rid of external fragmentation. Segmentation, though, logically divides memory into variable-size sections from the user's perspective, like your code, your data, and your stack. So the main takeaway: paging is fixed, segmentation is variable.
And that brings us to a massively tested vocabulary word, thrashing. Now, you know a page fault happens when a required page isn't sitting in main memory, right? Well, thrashing is the absolute nightmare scenario of that. It's when excessive page faults cause your CPU to literally grind to a halt. The system ends up spending way more time frantically swapping pages back and forth from the disk than it does actually executing your processes.
Moving right along to Section 4, Disk Scheduling Algorithms.
You really need to memorize the behavior of these algorithms to minimize disk head seek time. You've got first come, first served, which is super fair but pretty slow. Then shortest seek time first, which is faster, but you guessed it, can lead to starvation. But I want you to pay very special attention to scan. In scan, the disk head sweeps from one end to the other, servicing requests as it goes, literally exactly like an elevator going up and down a building.
Make sure you remember that elevator comparison for your MCQs.
And finally, Section 5, High-Yield Exam Numericals. Time to actually apply all this theory.
Okay, let's tackle the banker's algorithm matrix. This is going to look exactly like what you'll see on the exam. It's basically your ultimate tool for deadlock avoidance. Now, calculating the need matrix is always your first step. And it's simple. You just subtract the allocation values from the max values. So if we look at P0, a max of 753 minus an allocation of 010 gives us a need of 743. Once you've mapped out that need matrix, you just simulate granting those resources using your available vector to find a safe sequence so all the processes can actually finish.
When you're hit with paging address translation, do not panic. Just follow these 3 exact mathematical steps and you'll nail the physical address every time. Let's do a quick example. Say your logical address is 2500 and your page size is 1024. Step 1. Divide 2500 by 1024. That gives you a page number of 2. Step 2. Grab the remainder. 2500 minus 2048 gives us an offset of 452. Step 3. Let's pretend page 2 maps to frame 6. You just multiply 6 by the page size of 1024 and then add your 452 offset. Boom. Your physical address is 6596. See? Just simple structured math.
Now, for a first-come, first-served disk scheduling numerical, you're quite literally just serving requests in the exact order they arrive. All you have to do is calculate the absolute difference between the tracking requests to find the total head movement. So, if you start at cylinder 53 and jump to 98, that's an absolute difference of 45. Then, from 98 to 183, that's 85. You just keep adding up those absolute differences one by one until you get your final total. It's really that straightforward to prove a result, like, say, 640 total cylinders.
So, we've broken down the high-yield concepts that honestly dictate 90% of your practical exam. We went from the rigid rules of the critical section to the absolute differences in disk scheduling. But here's the ultimate question to leave you with. When you're sitting there and the clock is actually ticking, can you rapidly apply that banker's algorithm? Can you confidently calculate a physical address? Review these core commands, trust the structured steps we just went over, and you are going to absolutely crush your Virtual University CS604 Final.